WASP-76b is the kind of planet that makes you stop using the word weather and start using the phrase industrial accident. This world sits roughly 640 light-years away, and it is an ultra-hot Jupiter, a gas giant orbiting so close to its star that one full year takes about 1.8 Earth days. That tight orbit almost guarantees tidal locking, meaning the planet always shows the same face to its star. One hemisphere lives in permanent daylight. The other hemisphere lives in permanent night. On the day side, temperatures rise to roughly 4,350 degrees Fahrenheit. That is about 2,400 degrees Celsius. At that point, iron does not melt, it vaporizes. Iron atoms become part of the atmosphere, mixed into the flowing gas like humidity on Earth, except the humidity is metal. Observations with ESO's espresso instrument showed iron vapor on the hot side, and evidence it is transported toward cooler regions where it can condense. Now, picture what happens when that iron vapor is pushed by fierce winds into the night side. The temperature drops enough for the vapor to condense into liquid droplets, and those droplets fall as rain. Not water, molten iron. The same element we forge into bridges and engine blocks, falling from the sky in glowing droplets. There is something deeper going on here than shock value. These ultra-hot Jupiters are natural laboratories for atmospheric chemistry at extreme temperatures. On Earth, our chemistry is dominated by stable molecules. On WASP-76b, heat breaks molecules apart, and the atmosphere becomes a moving soup of atoms and ions. So when you hear iron rain, think of it as a sign that the atmosphere is crossing phase boundaries, gas to liquid, while racing around the planet at unimaginable speeds. It is a metal cycle happening in public. And that metal cycle sets the tone for this entire list. The cosmos is not short on planets. It is short on normal ones. Kelt 9b takes the temperature dial and snaps it off. This is another ultra-hot Jupiter, located roughly 670 light-years away. It orbits a hot A-type star every 1.5 Earth days. On the day side, temperatures exceed about 7,800 degrees Fahrenheit, and in some estimates creep even higher. NASA described it as hotter than most stars because many small red dwarf stars have surface temperatures below that number. At those temperatures, normal chemistry collapses. Molecules cannot stay intact. Hydrogen becomes atomic hydrogen. Metals do not just vaporize, they can ionize, meaning electrons are stripped away. The planet's upper atmosphere is more like a low-density plasma than air, and the planet is losing itself. Intense ultraviolet radiation from its star heats and puffs up the atmosphere, and the gas escapes into space. In a long-exposure view, you would expect a trailing cloud, a kind of atmospheric tail. The planet is literally being eroded by radiation. Kelt 9b is important because it is a boundary object. It is still clearly a planet by mass, but its physical behavior looks star-like. Studying it helps astronomers understand how atmospheres behave when they are heated beyond the limits that molecules can survive. It is a reminder that nature does not care about our category labels. Now, if you want the opposite kind of extreme, not heat, but darkness, meet TARES-2b. TARES-2b orbits a star about 750 light-years away. It became famous because it reflects almost no light. Its measured reflectivity is around 1% or even less in some models. In plain English, it is darker than charcoal. What makes a planet that black? The leading idea is that its atmosphere lacks reflective clouds and contains light-absorbing chemicals. Hot Jupiters can have sodium and potassium in vapor form, and those elements are very good at absorbing visible light. Meanwhile, at high temperatures, many cloud-forming compounds cannot condense, so the planet never develops a bright reflective layer like Jupiter's ammonia clouds. But here is the creepy twist. TARES-2b is not cold. It is hot, with temperatures on the order of thousands of degrees Fahrenheit. That means it can glow faintly red from its own heat, like a piece of charcoal that is black but still radiating. So you get this absurd combination, a planet that is visually void-like, yet thermally blazing. If you could hover above it, your eyes might not see much, but an infrared camera would see a glowing furnace. Darkness does not always mean cold. Sometimes it means efficient absorption, and absorption means heat. Now let's move to a planet that looks pretty until you understand what the blue actually is. HD 189733b is about 63 light-years away. It has been described as deep blue, almost Earth-like in color. But that blue is not from oceans. It is likely from light scattering off silicate particles in the atmosphere. Basically, microscopic glass. Your brain wants to interpret the color as water. The planet says no. This is another hot Jupiter, meaning the planet is huge, gaseous, and close to its star. The temperature is high enough to keep many compounds in vapor form, and at the same time to create aerosols that behave like a haze. Winds have been estimated at thousands of miles per hour, fast enough that if glass-like particles condense, they would be driven sideways with the force of a sandblaster. So when people describe glass rain, take it as a shorthand for something real. Silicate particles forming in a hot atmosphere, whipped by extreme winds. It is an atmosphere where even a tiny grain becomes a projectile. What's fascinating here is the physics of heat redistribution. On tidally locked hot Jupiters, winds transport energy from day to night. That circulation pattern is what makes exotic condensation possible, not just iron rain on dewy ASP76b, but potentially silicate condensation on worlds like this. These planets are telling us that when you lock a world to a star, you create a permanent climate engine, a conveyor belt of heat, chemistry, and violence. Now, let's visit a planet that is not just weird, it is actively being destroyed. WASP-12b is about 1,400 light-years away, and it orbits so close to its star that its year is about 1.1 Earth days. The orbit is so tight that tidal forces stretch the planet into an egg-like shape, and the star's gravity is pulling gas away from the planet. In effect, the planet is being eaten. Hot Jupiters are already puffed up by heat. WASP-12b is so puffed up and so close that the outer atmosphere is vulnerable. Gas can spill past the planet's gravitational boundary and form a stream toward the star. The system becomes a slow-motion transfer of mass. This is not only dramatic, it is a real clue about planetary evolution. Hot Jupiters probably do not stay stable forever when they are extremely close. Some may spiral inward, some may lose their atmospheres, some may be destroyed. WASP-12b gives us a front-row seat to a process that may be common in the galaxy, and yet invisible unless you catch a system at exactly the right time. Next, a planet that became internet famous for being made of diamonds, but is actually more interesting than that. 55 Cancri E is a super-Earth about 41 light-years away. It orbits its star in about 18 hours. That is not a typo. You could celebrate your birthday twice in a weekend there. Because it is so close, surface temperatures on the day side can exceed about 3,500 to 4,000 degrees Fahrenheit. Many models predict a vast magma ocean on the day side, a literal sea of molten rock. Early studies suggested the planet might be carbon-rich, and people ran with the idea that it could contain enormous amounts of diamond. The truth is more nuanced. The planet may be carbon-rich, but whether that translates into a diamond world depends on interior chemistry and oxygen availability. The safer statement is this: it is a tidally locked, ultra-hot, rocky world where rock is not stable. Rock melts, flows, and possibly evaporates. And here is the weird part: heat transport. Some observations suggest the night side is warmer than you would expect for a perfectly airless, locked lava world. That implies an atmosphere, or heat transport through magma flows, or both. In other words, this planet might have a rock ocean current, circulating heat like Earth's oceans, but with lava. Now, let's zoom out and talk about the largest ring system we have ever suspected around a planet. J1407b is a candidate companion with an enormous ring system, inferred from a complex dimming event observed in 2007. Researchers analyzing the light curve concluded that the ring system could span around 75 million miles in diameter. That is far larger than Saturn's rings, by roughly a couple hundred times in scale. This object is sometimes described as a super Saturn, but the key point is the ring system, which may actually be a circumplanetary disk, a structure associated with moon formation. The light curve suggested gaps in the rings, possibly carved by forming moons. Think of it as a lunar construction zone, a giant rotating blade of dust and ice. If you place that system where Saturn is, the rings would dominate the night sky. They would not be a thin line. They would be a glowing band spanning a huge fraction of the sky, with dark lanes and bright arcs. Even if J1407b's status is still debated, the observation is a reminder that we might be seeing planetary systems in the act of building their moons, and some of those systems are vastly larger than anything we see around the gas giants in our neighborhood. Now for a completely different kind of weirdness, a planet with two suns. Kepler-16b is a circumbinary planet, meaning it orbits a pair of stars instead of one. It is about 245 light-years away, and it is roughly Saturn-sized. If you could float in its upper atmosphere, you would see two stars rising and setting, sometimes together, sometimes apart, creating a sky that never repeats the same way twice. From a dynamics perspective, circumbinary planets are a triumph of orbital stability. Two stars create a time-varying gravitational field. Yet the planet maintains a stable orbit, showing that planet formation can occur even in messy gravitational environments. And it corrects a common misconception. Two suns does not automatically mean a warm desert world. Kepler-16b orbits outside the habitable zone. Its equilibrium temperature is far below freezing. It is not a vacation planet. It is a cosmic proof that nature can build stable systems in places we once thought were too chaotic. Next, a world that orbits a dead star. The PSRB 1257+12 system contains planets orbiting a pulsar, the ultra-dense remnant core of a massive star. Pulsars spin rapidly and emit beams of electromagnetic radiation and particles. This system is historically important because these planets were among the first confirmed exoplanets ever discovered. The weirdness is not just that planets exist there, it is that they exist after a supernova. One hypothesis is that they formed from fallback material, a disk of debris that remained after the explosion and cooled into planets. If you think of a solar system as something that forms once and then stays stable, pulsar planets ruin that story. They suggest second-generation planet formation, worlds that can form out of the wreckage of a dead star. Of course, the environment is brutal. High-energy radiation would be an ongoing threat. But as a physics object, it is extraordinary. It tells us planet formation is resilient. Now, let's lighten the color palette. GJ504b is a gas giant about 57 light-years away. It is sometimes called the pink planet because of its appearance in infrared and the way its atmospheric chemistry affects its emitted light. It is a young planet, still glowing with heat left over from formation. Its temperature is a few hundred degrees Fahrenheit, still lethally hot for humans, but cool compared to the ultra-hot Jupiters. Its atmosphere likely contains methane, water vapor, and other molecules that shape its spectrum. Why does this matter? Because it shows that planets do not just reflect starlight. Many directly imaged planets are seen because they emit their own infrared glow. Color, in this context, is temperature and chemistry, not paint. Next, a planet so fluffy it almost feels like a prank. Kepler-51b is part of a class often called superpuffs. These are planets with sizes comparable to Jupiter, or at least comparable to Neptune or Saturn, but with masses much smaller than you would expect. The result is extremely low density. If you could somehow place a superpuff planet into a gigantic bathtub, it would float. That sentence sounds silly, but it is a real implication of density. So what is going on? One idea is that these planets have extended hydrogen and helium envelopes that are heated and inflated by their stars. Another idea is that they are young, still cooling, still puffed up. Either way, their atmospheres are extremely extended, meaning they are vulnerable to atmospheric escape. They may be temporary objects, slowly shrinking as they lose gas. Kepler-51b and planets like it are a reminder that a planet's radius does not tell you what it is made of. Two planets can have similar sizes and be completely different in mass and structure. Now, a planet that rains rock. K2141b is a rocky exoplanet that orbits its star in about 6.7 hours. Yes, hours. That is one of the shortest orbital periods known for a planet. Its dayside temperature is estimated around 3,000 degrees Fahrenheit or higher, hot enough to melt rock. On the dayside, you likely have a magma ocean, but it gets stranger. At those temperatures, some minerals can vaporize. Rock becomes gas. That gas rises, moves toward the night side, cools, and can condense. So you could have a literal rock cycle. Vaporized silicates transported by winds, then condensing and falling back as droplets or grains. Not water rain, rock rain. And because the planet is tidally locked, the day side and night side could be in constant exchange, with molten rock evaporating and recondensing, like a bizarre planetary distillation system. Now, let's return to the pressure nightmare. GJ436b, the burning ice world, because it deserves one more layer of explanation. When you hear ice that burns, the key is phase diagrams. On Earth, we deal with pressures around 1 atmosphere at sea level. Inside Neptune-sized planets, pressures reach millions of atmospheres. Under those pressures, water becomes exotic. Ice X is one phase. There are others. Some phases conduct electricity. Some become superionic, where oxygen atoms lock into a lattice while hydrogen ions move freely, creating a material that is part solid, part liquid. So GJ436b may not just have ice. It may have exotic ice that behaves like nothing we have in daily life. It is a world where water is not familiar. It is a high-pressure mineral. Now, let's end close to home with a planet that is weird because it could have been Earth-like, and then took the worst possible turn. Venus is our neighbor, and it is the clearest example of how two planets can start similar and end completely different. Venus is roughly Earth's size. It is sometimes called Earth's twin, but its atmosphere is almost entirely carbon dioxide with clouds of sulfuric acid. The surface pressure is about 90 times Earth's. That is like being nearly a mile underwater in terms of crushing force. Surface temperatures hover around 870 degrees Fahrenheit. And the reason is a runaway greenhouse effect. Once Venus lost stable oceans, water vapor, a greenhouse gas, amplified heating. Heat caused more evaporation. More evaporation caused more greenhouse trapping. Eventually, the system ran away, and the planet became a sealed pressure cooker. Venus is weird because it is not exotic in composition. It is exotic in outcome. It is a warning that climate feedbacks can push a planet across a threshold. So when you look at all these worlds together, you start to see a theme. Some are weird because of heat, some because of darkness, some because of pressure, some because of orbital architecture, some because they are being destroyed. Some because they do not even have stars, and all of them are real enough to have left fingerprints in light, spectra, timing, and gravity, the tools we use to study worlds we will not visit for a very long time. If you want more tours through the universe's strangest real places, hit like and subscribe. The galaxy is full of worlds that sound fictional right up until the data says otherwise.